Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like half and full adder circuits, RS flip-flop, JK flip-flop. Slide 1. Introduction to adders and flip-flops. Let us begin by understanding two fundamental digital components, adders and flip-flops. Adder circuits are basic combinational logic circuits used for arithmetic operations. Specifically, they add binary numbers. You'll find them in every digital calculator and processor. The half adder is the simplest adder, used to add two single-bit binary numbers. It provides two outputs, sum and carry. The full adder is an improved version that can add three binary inputs, 2 bits and a carry in from the previous operation. Now let's talk about flip-flops, which are sequential circuits, meaning they remember previous states. A flip-flop is a circuit with two stable states. It can store one bit of data, either 0 or 1. The RS flip-flop stands for reset set flip-flop, and it's the most basic type. It uses two inputs to either set or reset the output. The JK flip-flop is a universal flip-flop. It corrects the limitations of the RS flip-flop and supports a toggle mode. Both adders and flip-flops are essential building blocks in digital systems, for calculations and data storage respectively. Slide 2. Half adder circuit. A half adder is the simplest circuit that can perform binary addition of 2 bits. It takes two 1-bit inputs, named A and B. It generates two outputs, sum, which is the result of a plus B without carry in. Carry, which is generated only when both inputs are 1. How does it work? Sum is obtained using the XOR gate. XOR means the output is high, 1, if only one input is high. Carry is generated using the AND gate. It outputs 1 only if both inputs are 1. For example, if we add A equals 1 and B equals 1. XOR gives sum equals 0. And gives carry equals 1. So the result is binary 10, carry equals 1, sum equals 0. Limitation. It cannot add carry from a previous digit. That's why it's not enough for multibit operations. Slide 3. Full adder circuit. A full adder addresses the limitation of the half adder by adding a carry in bit along with two input bits. Inputs A, B, and C in, carry in from a previous addition. Outputs sum and carry out. How does it work? First, it adds A and B using a half adder. Then, it adds the intermediate sum to C in using another half adder. The carryout is obtained using an OR gate on the carries from both half adders. Equations. Sum equals A XOR B XOR C in. Carry equals A and B OR C in and A XOR B. Example, A equals 1, B equals 1, C in equals 1. Sum equals 1, carry equals 1. Right pointing arrow result is binary 11. Advantage. Can be connected in series to perform addition of multibit numbers, like 4-bit adders used in CPUs. Slide 4. RS flip-flop. Now, let's move on to sequential logic, starting with the RS flip-flop. RS flip-flop has two inputs, S set and R reset. It has two outputs, Q main output and Q inverted output. It is constructed using NOR or NAND gates. It's the most basic memory element, stores 1 bit. However, the invalid state 1, 1 makes it unreliable in some situations. Example, in a device where a button toggles on, off, an RS flip-flop can store whether the device is currently on, Q equals 1, or off, Q equals 0. Slide 5. JK flip-flop. To overcome the problem of the invalid state in the RS flip-flop, the JK flip-flop was developed. It has three inputs, J, K, and a clock. The clock signal controls when the flip-flop checks the inputs. The toggle means the output changes to the opposite of its current state, 1 becomes 0, 0 becomes 1. This makes it ideal for counters. Clock JK flip-flop only responds when clock pulses are applied, providing synchronous operation. JK flip-flops are called universal flip-flops because they can act as RS, D, or T flip-flops by adjusting input conditions. Example: used in binary counters and timers where toggling is required with each clock pulse. Slide 6. Differences: half adder vs full adder vs flip-flops. 1. Function: half adder adds 2 binary bits. Full adder adds 2 bits and 1 carry in. Flip-flop stores 1 bit of data. 2. Inputs: half adder takes A and B. Full adder takes A, B, and C in. Flip-flop takes set, reset or J, K with clock. 3. Outputs: half adder gives sum and carry. Full adder gives sum and carry. Flip-flop gives Q and Q, complement of Q. 4. Carry handling: half adder does not accept previous carry. Full adder can add previous carry in. Flip-flop does not handle carry. 5. Components used: half adder uses XOR and AND gates. Full adder uses 2 half adders and an OR gate. Flip-flop uses NAND or NOR gates. 6. Application: half adder is used in simple addition logic. Full adder is used in binary calculators and ALUs. Flip-flop is used in memory units and counters. 7. Clock requirement: half adder is a combinational circuit, no clock needed. Full adder is also combinational, no clock needed. Flip-flop is a sequential circuit, needs clock input. 8. Example: half adder: 1 plus 1 equals binary 10 right pointing arrow sum 0, carry 1. Full adder: 1 plus 1 plus carry 1 equals binary 11 right pointing arrow sum 1, carry 1. Flip-flop stores logic 1 or 0 and changes on clock. 9. Complexity: half adder is simple and basic. Full adder is moderately complex. Flip-flop ranges from simple, RS, to advanced, JK.